Hello, welcome to numerical ship and offshore hydrodynamics. So, today we have lecture 29 and today we are going to discuss on the Cummins equation, which is popularly known as time domain panel method using impulse response function. Okay. So, to get this lecture you have to use these keywords. Okay. So, let us go to the topic. Now, today all the discussion I am making from this paper by Cummins 1960, very famous paper, and if you look at this below link you can use this link to download that paper. Okay. Now, in fact, this Cummins equations or the impulse response functions is very popular in the domain of electronics. They use this some impulse response functions to get signals, transfer functions. He first realized that concept that is there in the field of electronics can be incorporated in the case of finding out the response of a ship also. Okay. But however, this paper mostly based on most of the thing based on the mathematical derivation to finding out the solution is consistence or uniqueness everything, but somehow lacking some physical explanation. Later on Ogilvy 1964 I guess he actually in from physical aspect he discussed this Cummins equations, and till that point nowadays it is a very standard equation or standard method to find out the motion of a vessel. Okay. Without further delay, let us see some key aspect of it. Okay. So, now you can see there is a glass and the water, and let us see that what is happening if I throw some either stone or it is not possible or some ice cube here. Okay. It is very nice thing to see. Now, this is coming, and then you can see that there is a excitation in the water surface. Now, thing is that remember I throw the ice cube at t equal to 0, let us assume. Now, you can see that even if actually now the ice is not moving inside the water, it is cool and calm, but if you look at the free surface, the free surface actually still you can see a lot of waves are there. Now, this is a very important this is a very important understanding that you have to very clear about this. Now, the difference between the water below the free surface and that the water on the free surface, the difference is in below that water if you move a body or if you move a particle, we have discussed in infinite fluid domain, then the moment you stop the body, then surrounded particle they do not oscillate, they stop. However, that is not the same in case of a free surface. Now, I just throw the ice at t equal to 0, but I can see the wave is still continue in quite some time. So, it means that it has some kind of the what to say that effect of throwing the ice into the water at t equal to 0, but still it has some effect at after some times it is really do not die down. Now, you can see here even if after quite of some time it is still oscillating, right. Now, since slowly this ice cube is coming out on the free surface. So, this ice also starts oscillating with respect to this body, but you can see it very slowly actually it is dying down. So, it means that that wave it created at t equal to 0, and then this wave will continue for quite some time. So, then now this is something he can relate this with kind of a memory effect. Now, what is that memory effect? Let us now try to see this, and then let us try to discuss the same. Okay. So, remember this is the paper, that this is a link you are going to get this paper. Now, let us go back to the physical explanation of this phenomena. So, now what actually I showed you that that a body that or a thing actually, suppose this is let us say surface of a, I mean this is some tank, and then you have some water over here, okay. And then if you throw some object, then what is happening that you can get some kind of wave. Now, what is happening that even if you throw this stone, let us say at t equal to some time t 0, okay, and then this waves is continue with quite some time, it is maybe some t 0 plus some n into delta t. So, it is a quite some time it start oscillation, right. Now, keeping that in mind, and we call basically that as a memory effect. Why I am calling this memory effect? Let us try to understand it. Now, keeping in mind this fact, okay. Now, assume a system, a linear system. Now, assume a linear system, okay, and assume that this the fluid is inviscid and the flow is irrotational, homogeneous, incompressible, everything, so that we can define a potential function. We can say the capital phi, let us say, is a potential function, the total potential that when you throw the ice cube or throw a stone inside the water. Let us assume that. Okay. So, I am doing in with respect to the potential theory. Okay. Now, if you assume this, now now let us take at very tiny time, at let us say at delta t 0, okay. Then because of this, if I throw the stone or ice into the water, what I am essentially doing, I am displacing the water particle from its calm steady mean position, right. Now, when I do that, let us say that I am doing some impulsive displacement which is delta x, and then this velocity at the velocity actually I am throwing the stone or the ice cube in this water, let us say this is a constant velocity v. Okay. Now, needless to say that this disturbance in the water depending on the velocity. If I put in a more velocity, right, then actually I can get the displacement more. If I throw it a less velocity, definitely I can get the less displacement, right. So, therefore, let us assume another velocity potential psi. If you remember that always we define a velocity potential equal to the velocity potential or normalized velocity potential multiplied by the some magnitude. Now, that is what we have done in case of a Wamid based solution. Remember that time I defined this phi equal to some xi multiplied by the psi, where this psi is basically the velocity potential for the unit amplitude of the motion, right. This is well known that we have done in our previous lecture. Please get this previous lecture where actually I have defined that my velocity potential phi j equal to some xi j multiplied by the psi j, where I define this psi j is nothing but the velocity potential for unit amplitude of the motion. Now, having said that we know this concept, so definitely this psi we can call this a normalized velocity potential. Okay. So, therefore, if it is a normalized velocity potential, then this total velocity potential phi can be equal to this v, which is the magnitude that which I am throwing the object, multiplied by this normalized velocity potential psi, right. Now, if you have the 6th mode, then we can say that v j equal to the phi j equal to v into psi j, but when it is it is when this your time is t 0 less than t less than equal to t 0 plus delta t. So, I am taking a very small interval from t 0 to t 0 plus delta t, and in this small interval actually I am throwing the stone or anything, any object, right, and then actually I get some disturbance, and this disturbance I am telling this disturbance is proportional to the velocity. So, if you add more velocity, the disturbance is more. So, then and if psi j be the you can say the velocity potential for unit amplitude of the velocity, then and if phi j be the total velocity potential, then phi j equal to v into psi j, right. So, then actually I come up with a equation v into psi, or let us take a single degrees of freedom, let us not take this all the multi degrees of freedom motion, let us go for a single. So, that is why I can drop the index j, simply I can write phi equal to v into psi, where at which time when t 0 less than equal to t less than equal to t 0 plus delta t. So, this is let us take this is my equation number 1. Okay. Clear? Now, the fun part is that when I show you the video, even if you drop it, but then you can see the wave is continue. Now, if you so let us take assume that at each, let us now take a block here, let us take some blocks. Okay. Now, let us take it is t 0, now it is definitely t 0 plus delta t, then it is t 0 plus 2 delta t, then this block is t 0 plus 3 delta t, then maybe it is t 0 plus 4 delta t, and then so on, it is let us say t 0 plus n delta t, let us take. Now, what is happening, suppose I am throwing this velocity v. Now, this velocity v I am throwing throughout. Okay. So, then here definitely I can get my psi my phi is equal to v into psi, and that is I am doing in between t 0 less than equal to t less than equal to t 0 plus delta t. Now, let us assume that again I am throwing a the body or at any object in between the time t 0 plus delta t. Now, when I am doing it, what is going to happen? See here that definitely there is another, I can see that in this time frame also I have, let us take this velocity potential phi, this equal to not only this v into psi for that particular interval of time. So, you can say this psi of it is now it is t 0 plus delta t comma t 0 plus 2 delta t, right. Definitely this is like this. However, still this velocity potential is not complete. Why? Because I have throw a stone or the same body just in the time interval of t 0 comma t 0 plus delta t. Now, if you are referring to my video, now you can understand that wave has effect here also, and that effect is called the memory effect. Okay. Now, thing is that I throw again a stone at t 0 comma t 0 plus delta t in that time frame. However, that wave is not is the only sole wave, because this also this total potential is not because of I throw a stone in the time interval t 0 plus delta t comma t 0 plus 2 delta t, also it has a effect the wave that when I throw a stone in t 0 comma t 0 plus delta t. That means, here I have two effect, one is some effect, it is this the primary effect plus some effect which is coming from the previous time step. Now, how to measure this one, right, how to measure this one. And similarly, if I now let us for this in this case, I can write my total potential phi equal to V in some psi in this time interval t 0 plus 2 delta t comma t 0 plus 3 delta t, right. So, but this is not the total potential, right, but this plus I have to add like some k equal to 1 to 2, because this is my previous to situation I can throw the stone. So, that effect also I need to consider, right. Now, let us try to find out how actually I can get the second part of it. So, first part is clear to me, each time I am throwing with a constant velocity v, and because of that I am getting some kind of disturbance, and I am calling it, that is the phi, I mean the velocity potential is v multiplied by that psi j, where psi nothing but the velocity potential of the, or normalized velocity potential, or I can say velocity potential for unit amplitude of the velocity, right. But then what is the other part? Now, if you think carefully, like when actually you have more effect, like if I start here I am just excite that body, then how far you can expect that effect will go, right. Now, if you look at this my previous video, it lasts for some 5-6 seconds I guess. Now, when you think that it could last not 5-6 seconds, it will end maybe around some 10-11 seconds or maybe some 15 seconds. How? So, the only answer is if that impulsive displacement is more, right. So, that means if I do more impulsive displacement, then my memory effect will more. So, then actually in the second part I can assume the psi since it is varies us with the impulsive displacement, which is delta x. So, therefore, again I can define a normalized velocity potential chi in that case also, and I can simply say this phi is nothing but chi into delta x, and when these effects last for when t greater than equal to t 0 plus delta t, let us say. Okay. So, now actually I am ready to write a general expression. So, then I can write my phi now let us take a uniform, let us take not uniform, let us take a general time interval at t n comma t n plus delta t. Let us take a general interval t n comma t n plus delta t, and now I am interested to write a velocity, complete velocity potential because of that. Now, if I write this, how do I write it? So, definitely I can write that I am throwing some, let us say some v at, let us take that nth time step, and then I multiply with the psi. So, this is the first thing I would do, and then plus I can take the effect, it is coming from the from the start. So, I can write the summation which is k is equal to 1 to the n, actually the present time step, right. So, I have to count all the effect of because of this, and this nothing but I can write this chi, we can call it as a n minus k into multiply by the some impulsive displacement at dxk delta xk, something like this, right. And again this, now I know that now the displacement equal to velocity multiplied by the time. So, definitely I can change this to this into some velocity into v k and also the delta t. Okay. So, this is how actually I can write it. Okay. So, that means here these things I call it is a memory effect, and these things I call that when actually I throw the stone, that disturbance is coming from this particular expression. Okay. So, now this is maybe it is let me write it finally, it should be V n into psi. So, see I am dropping the index. Okay. So, I am assuming it is a single degree of freedom motion. So, therefore, I am dropping this jth index, otherwise it should be the j. Okay. K is equal to 1 to n and chi n minus k into V k into delta t. Okay. Now, what is what? So, you can define what is V n. V n is nothing but the velocity at the nth time step. Psi is the velocity, normalized velocity potential for this, and then what is the chi n minus k? Chi n minus k is nothing but the velocity potential in for the time interval, it is t n minus sorry, it is t n comma t n plus delta t, and then V k is basically the velocity at in the interval t n comma t n plus delta t. So, this is how actually I define the notation is given. So, V n is the velocity at nth time step, x n minus k is nothing but the velocity at t n comma t n plus delta t time step, and V k is nothing but the velocity at t n comma t n plus delta t time instant. Now, if you take delta t goes to 0. So, now let me write in the differential form. So, if you write in the differential form, I can get that phi t, which is the present time step, is nothing but the velocity at the present time step multiplied by the psi plus the memory effect. Now, if you remember, for the discrete case, the memory effect starts from k equal to 1, right. So, let me write over here that memory effect is summation k is equal to 1 to the previous times n, which is chi n minus k multiplied by the V k into delta t, right. If you remember this, now I can write the integral form, it is minus infinity, because when you do the integration, when it started is minus infinity to the present time step n, which is t. So, then I replace that chi, it should be t minus tau, tau stand for the k, okay, and then it is x dot tau and integration definitely with that respect to the tau d tau. So, this is how I can write the expression for the velocity potential phi. Now, when I write the expression for the velocity potential phi, then how I get the pressure? So, pressure P definitely it is minus rho into del phi by del t. Okay. So, now I have to differentiate the whole thing with respect to t. So, I can get my pressure equal to minus rho into x double dot t multiplied by the psi plus del del t of minus infinity to t into chi t minus tau x dot tau into d tau. Now, here tau is not the function of t. So, therefore, further I can write the pressure P equal to minus rho into x double dot t into psi plus minus infinity to t. So, I can write del del t of chi t minus tau and then multiply by the x dot tau into d tau, fine. So, now if this is the pressure, then how I can get the the force. So, now when you look at the force is nothing but the pressure multiplied by the normal direction n, right. So, now if I try to find out the force in this case, so it is nothing but minus rho. So, integration over the S, and I have to substitute my that pressure, which is x double dot T into psi plus minus infinity to T into del T into chi T minus tau into x dot tau into d tau, right, and then whole ds. So, now I just need to rearrange this little bit. Okay. So, let me rearrange as follows. This is now, let us rearrange it, minus rho over the s, okay, and then I just here it should be n into ds. Okay. So, then it is psi dot n into ds. I just multiply x double dot T, and for the second part what I do is it is plus, now it is minus over here. So, I just make it plus and then I just make minus rho into okay, let us make it minus infinity to T, it is minus rho in, and then I just do the surface integral over S, it is minus rho, then it is del tau, it is T minus tau multiplied by the n, right, and if whole in ds, and then the everything here should be multiplied by the, it is x dot tau into d tau. Now, why I am doing it? I am doing it because I need to write this term of a added mass multiplied by the acceleration. Now, here this term actually I can call as a added mass A. Okay. And similarly, if you look at this term, the term inside this surface integral, I can call this as a, you know, the damping term. Now, here I can call this as a, you know, B into T minus tau, the whole thing. Okay. So, therefore, I can write for the second term is minus infinity to T, it is B T minus tau into x dot tau into d tau. Okay. So, therefore, this force I am writing in terms of added mass and the damping. This term is related to the damping and this term is related to the added mass. Okay. So, therefore, you see this is force is called the radiation force. So, therefore, finally, I could now able to write my radiation force F in term of A into x double dot T plus a memory function which is minus infinity to T into, I can call B T minus tau into the x dot tau into d tau. Now, unlike in general in frequency domain, we do not have this memory effect. So, physically speaking, this added mass is coming due to the fact that I am throwing the body at each instant of time t, and the second component is coming because of the I am throwing the stone at, let us say, t0 time. So, consider the memory effect when actually I try to evaluate the motion at the body at some particular time Tn, right. So, these things we call as a memory effect. Remember, I am telling again, here this part, let us consider this part, this is the added mass, this is because actually I am throwing the stone at the time Tn, and this will actually the cumulative effect when actually I start throwing the stone from T0 till the time Tn. So, it is taking all this memory effect, and then if I add together, I get the complete radiation force. Okay. So, today let us discuss this, stop here. Now, this is the link, and you can get this paper through this link. However, this physical explanation not given in this paper of course, but actually you can get the mathematical insight like if this equation is consistent or not, and how to find out the motion, how to get the body, everything is written in this paper. Okay. So, therefore, let us stop today. Thank you very much.